I had a moment yesterday. I was sitting there. I had ChatGPT open in one tab, writing this really difficult email,
Hmm.
and then I was using Google Translate on my phone to figure out a label on this jar of like imported sauce, and my voice assistant was reminding me to take the pasta off the stove, and I
It was a
stopped.
moment of
It
realization.
was a realization that this stuff isn't just coming anymore. It's here. I mean, it's the background radiation of our entire digital life. It's in the
Hmm.
browser. It's in our pocket. It's writing code.
Yeah.
But here's the thing that bugs me. We all use it. We know it works. I type a prompt. I get an answer. But I feel like 99% of us, myself included, kind of treat it like a magic trick.
You put a coin in the box and a dove flies out.
Exactly. But it's not magic. It's engineering.
Yeah.
And honestly, it's engineering that feels like it shouldn't work as well as it does. So today, I want to stop looking at the dove and, I want to take apart the box. I want to ask, how does a machine actually understand language?
It is a great question. And to answer it, we have to talk about one specific architecture, the transformer.
It's a transformer. And just to clear the air immediately, we are not talking about Optimus Prime.
Although, interestingly enough, the name isn't a total coincidence. We are talking about a neural network architecture introduced by Google researchers back in, 2017. They released a paper that I think has one of the most confident titles in the history of computer science. Attention is all you need.
I love that title. And I found a fun fact in the notes. That title is actually a direct riff on the Beatles song All You Need Is Love.
It is.
And the team at Google who wrote it, they called themselves Team Transformer internally. Apparently one of the authors, Jacob Uskerite, just liked the sound of the word transformer. It's just wild to think that a little pop culture pun ended up naming the technology that effectively rebooted the entire tech industry.
It really, really did. But the title, Attention is All You Need, wasn't just a catchy hook, it was a hypothesis, a very aggressive one. They were basically claiming that if you just pay attention to the data in a specific way, you don't need all the complex loops and, memory structures we used to rely on.
So our mission for this deep dive is to unpack that hypothesis.
Yeah.
We're going to tear apart the brains of this architecture, figure out why the old way of doing AI kind of hit a wall, and understand why this new roundtable approach changed everything.
Sounds like a plan.
Okay, let's start with the before times. Because to appreciate the transformer, you have to understand the misery of what we had before. Before 2017, if you wanted to translate English to French, what were you using?
You were likely using RNNs, recurrent neural networks,
Huh.
or maybe LSTMs, which stands for long short-term memory networks.
RNNs. The best analogy I found for these, and shout out to Reddit for this one, is the factory assembly line.
That is a very, very apt comparison.
So help me build this visual. Imagine a factory line. You have a row of workers, these are your neurons, and the sentence comes down the conveyor belt, let's say. The quick brown fox jumps over the lazy dog.
Okay.
The first worker grabs the first word, the. They process it, and then they whisper what they learned to the second worker.
Right. And in technical terms, that whisper is crucial. That's the hidden state. It's the context being passed forward.
So then the second worker takes the word quick, combines it with the whisper from the first guy, processes it, and then whispers to the third guy. It's all sequential.
And for short sentences, this works fine. Hello, how are you? The whisper makes it to the end intact.
But here's the flaw in the factory line. By the time that whisper gets to the worker handling the word dog at the very end, especially if we're talking about a long paragraph,
Yeah.
the message is garbled. It's like a game of telephone.
Exactly. We call this the vanishing gradient problem. The signal from the beginning of the sentence becomes so weak by the time you reach the end that the network effectively forgets the subject. If you write, Alice, who was born in Paris, grew up to be a scientist, and then 50 words later you use the word she, an RNN really struggles to remember that she refers to Alice.
It forgets the beginning by the time it reaches the end. But there's another problem, isn't there? It's not just forgetful, it's slow.
It is incredibly inefficient for modern hardware. Think about a GPU, a graphics processing unit. I mean, these chips are designed to do thousands of calculations at the exact same time. They love parallel tasks.
But the factory line is sequential.
Precisely. Worker number 5 cannot start their job until worker number 4 is done. So you have this massive, powerful GPU just sitting there, sort of tapping its foot, waiting for the previous word to be processed. It's a massive bottleneck.
So enter the transformer. And this is where we pivot to the round table analogy.
Right. Blow up the factory. Fire the line manager. Instead of a line, imagine a massive circular conference table.
And the words of the sentence aren't coming down a belt anymore.
No. Every single word in the sentence, or the paragraph even, is sitting at the table simultaneously.
So Alice is sitting right across from she, even if they're 50 words apart in the text.
Yes. And more importantly, everyone at the table can pass notes to everyone else at the exact same time.
That is a fundamental shift.
It is. The technical implication here is parallelization. The model doesn't have to wait. It ingests the entire sequence at once. This is why tools like ChatGPT can be trained on basically the entire internet. If they had to read the internet one word at a time, sequentially, well, we'd still be waiting for the training to finish.
So speed is a huge factor. But just staring at each other isn't enough. I mean, if everyone at a table shouts at once, that's just noise. The paper is called Attention is All You Need. So how does the model decide who to listen to?
This is the secret sauce. Self-attention. It's the mechanism that allows a word to look around the table and say, okay, who here is relevant to me?
Let's ground this with an example, because this is where it gets abstract. I love the example from the illustrated transformer. The sentence is, the animal didn't cross the road because it was tired.
Simple enough for a human. We know it refers to the animal.
Right, because roads don't get tired. But a computer doesn't know biology or physics. To an old RNN, the word road is actually physically closer to the word it in the sentence structure, so it might get confused.
Correct. But the transformer does something different. When the model looks at the word it, the self-attention mechanism assigns a score to every other word at the table. It looks at road and says low relevance. It looks at animal and says high relevance.
So it effectively highlights the word animal.
It does more than highlight. It takes the meaning of animal and sort of mixes it into the representation of it.
So by the time the processing is done, the word it isn't just a generic pronoun anymore. It carries the flavor of the animal.
That's a beautiful way to put it.
But, and I know our listeners well enough to know they are screaming at their speakers right now, how does the math know that animal and tired go together? It doesn't have a brain. It's just numbers.
This brings us to the most intimidating, but arguably the most brilliant part of the architecture. We have to talk about vectors, specifically query, key, and value.
Q, K, and V. I saw these in the research notes. I almost closed the tab. But then I found the search engine analogy, and it clicked. So walk us through this.
It's the best way to visualize it. Think about how you use a library database or a search engine like Google.
Okay.
You have something you want to know. You type it into the search bar. That is your query. Q.
So in our sentence, the word it creates a query.
Exactly. The word it generates a query vector that effectively asks, what noun in this sentence is capable of being tired?
Okay, so it broadcasts this query. Now what about the other words?
Every other word in the sentence, animal, road, cross, is holding up a label describing itself. That label is the key, K.
So animal is holding a key that might look mathematically similar to concepts like living thing, biology, subject. And road holds a key like inanimate, concrete, location.
Simplistically, yes. Now, the model performs a calculation called a dot product. It's just a fancy way of measuring similarity between two lists of numbers. It compares the query from it against the key from road.
And I assume they don't match.
Yeah. Very low score. The dot product is small. The model says, ignore this.
But when the query hits the key for animal,
Bingo. High score, high attention. The math says these two concepts align.
and once it finds that match, what happens? Does it just flag it?
It does one more step. It retrieves the value, V. If the key is the label on the book, the value is the actual content of the book. The model takes that value, the rich meaning of animal, and pulls it into the context of it.
That is incredibly clever. It's
Yeah.
like every single word is constantly running a Google search on every other word in the sentence to figure out its own context.
And it's doing this billions of times. And remember, it's not just doing one search. This is where multi-head attention comes in.
The Hydra.
The Hydra, yeah. You imagine you don't just have one librarian looking for the answer. You have 12. Or in the big models like GPT-4, you have 96 heads.
And they aren't all looking for the same thing.
Exactly. One head might be strictly looking for grammatical relationships, finding the subject and the verb. Another head might be tracking gender. Another might be looking for, I don't know, emotional tone.
So you get this layered, nuanced understanding. It's not just word A matches word B. It's a 3D map of the language.
Right. It ensures that the model doesn't just get the literal meaning, but the subtle contextual meaning.
Okay, I'm with you on text. It reads the whole book at once. It uses search queries to connect words. I get why it's good at writing essays. But here is where the research took a left turn that I did not expect.
You're talking about vision.
Yeah. You're talking about sentences and grammar, but the source material talks about vision transformers VIT. How do you feed a photograph into a system designed for words? You can't type a sunset.
You can't. But remember, the transformer doesn't actually care about words. It cares about sequences of data. It cares about tokens.
So how do you turn a picture into a sequence?
You chop it up. We call them patches. Imagine taking a photo of a cat and cutting it into a grid of little 16 by 16 pixel squares.
Oh, like a mosaic. Or cutting up a magazine page.
Exactly. Now, you take those little squares, you flatten the pixel data into a list of numbers, and you feed it into the model. To the transformer, that little square of the cat's ear is just a word. It's a token.
So it applies the same roundtable logic.
The exact same logic. The patch with the cat's ear sends out a query. It looks for keys in other patches. It finds a high match with the patch containing the cat's tail or the whiskers.
So it learns the grammar of an image.
It learns spatial relationships.
Yeah.
It learns that ears usually go on top of heads. It learns texture.
This explains why we see things like DeepSeek OCR mentioned in the notes.
Yeah.
It's blurring the line between seeing and reading.
Exactly. DeepSeek uses vision tokens to reconstruct text. It's not reading the letters one by one like the old OCR software. It's looking at the image of the text and understanding the structure.
And honestly, once you realize everything can be a token, the floodgates just open. I saw code generation. Obviously, code is a language. That makes sense.
Wow.
Yeah.
This is the frontier. The Titans paper touches on this. A DNA sequence or a protein. What is that?
It's a sequence of letters. GATC.
Exactly. It's a language. Transformers can look at a string of amino acids and use attention to predict how that protein will fold in 3D space.
Because the folding depends on how different parts of the molecule interact with each other. Just like the word it interacts with animal.
Physics is just the grammar of the universe.
Okay, that is profound and slightly terrifying. We have this universal processing engine, but let's pump the brakes. Is it perfect? Because I still see these models making up facts, getting math wrong, going off the rails.
We have to talk about the elephant in the room, hallucination.
The polite term for lying to my face.
Well, here's the controversial take from the Stanford lecture material. Hallucination isn't a bug. It's arguably a design choice.
Wait, hang on. We designed them to lie. That sounds counterproductive.
We designed them to predict. That's the distinction. The model is not querying a database of facts like Wikipedia. It is a probability engine. It asks, given the words I've seen so far, what is the most statistically likely word to come next?
So if I ask for a biography of a fake person.
And it writes a totally convincing, beautiful biography. It has succeeded. It's successfully predicted a sequence of words that sounds like a biography. It doesn't know that the person doesn't exist. It doesn't know what exist means.
That is a crucial mental shift. It's prioritizing fluency over factuality.
Always. And that leads to another big risk mentioned in the notes, model collapse.
This is the Ouroboros problem, right? The snake eating its own tail.
Exactly. If the internet gets flooded with AI-generated content, which is happening right now, and the next generation of models trains on that content.
It's like making a photocopy of a photocopy.
The signal degrades, the nuances vanish, the eccentricities of human language, the weird slang, the creative errors get smoothed out into this, beige average mush. The models effectively get dumber because the training data loses its diversity.
There's also the cost. We talked about the round table where everyone talks to everyone. That sounds expensive.
It is extremely expensive. Technically, we say attention has quadratic complexity, meaning if you double the length of the document you want to read, the amount of computation doesn't just double, it quadruples. If you triple the length, it goes up by 9 times.
So reading a whole book is exponentially harder than reading a chapter.
It hits a wall. This is why you see context limits. It's why you can't just paste a 500-page legal contract into the older models and expect it to remember the first page by the time it gets to the last without burning through a massive amount of compute.
So that brings us to the future. If the transformer is the king, but it has this quadratic cost problem, is there a usurper coming?
There are tweaks. You mentioned flash attention earlier. That's a hardware optimization to just move data faster so the cost hurts less. But the really exciting stuff is rethinking memory entirely, like the Titans architecture.
Titans. It sounds like a Marvel movie. What makes it different?
It tries to solve that short-term memory problem. Instead of just the round table where everything is immediate, Titans introduces a neural memory module. Think of it as long-term memory.
And this is where the surprise metric comes in, right? I found this fascinating.
Yes. This is based on a theory of human psychology. Think about your commute to work this morning. Do you remember every single car you passed?
No, absolutely not. It's a blur. I was on autopilot.
But if a zebra had run across the highway,
I would definitely remember the zebra. I'd probably be tweeting about it right now.
because it was surprising, it broke the pattern. Titans tries to do this. It measures the gradients, effectively the error or surprise of a piece of data. If the data is predictable and routine, it handles it lightly. If it's surprising, it updates the long-term memory.
That is remarkably human. It's efficiency through ignoring the mundane.
Exactly. And this is key for what we call agents.
Agents, meaning AI, that can actually do things over long periods.
Right. If you want an AI to plan a vacation for you, that takes days of back and forth, checking flights, remembering preferences. It needs a memory that lasts longer than the current conversation window. It needs to remember the zebras of the task without getting bogged down by every detail.
And combining that with multimodal capabilities, seeing, hearing, reading all at once, it feels like we are inching closer to something that looks less like a text generator and more like a digital collaborator.
We are, but if I can synthesize all this, Transformers gave us the ability to find patterns in chaos. Whether that chaos is language or pixels or DNA, they moved us from the assembly line to the round table.
But the deep dive takeaway for me, especially after hearing about the hallucinations, is that they are still just math. They are engines of probability, not truth machines.
Precisely. They can give you the value, but only if you provide the right query.
The machine pays attention to the data, but we have to pay attention to the machine.
Now that's the job for the next decade.
Well, that gives us plenty to think about next time that little cursor is blinking at us. A billion-parameter round table waiting for a prompt.
It's a powerful image.
Thanks for unpacking it with me. And to everyone listening, thanks for diving deep. We'll catch you on the next one.